Hi everyone, this week we are going to get into the machine learning aspect of the course. First, we're going to talk about model selection. What is model selection? So, predictions can be built in many different ways. We went through different methods before. We also talked about including different variables. In each estimated model will yield different predictions. We saw that some estimators can be used over others. That is usually justified by assumptions. For instance, using IV estimators if we expect some endogeneity issues, using some GLS procedure if we expect heteroscedasticity, and so on. Now, assumptions are going to justify which estimator to use. Yet, we are not done yet. Once we choose an estimator, which variable should we include besides the one of interest? Of course, it is going to depend on our objective. Do we want to predict? Do we want to estimate? So in this lecture, we are going to compare models in order to select the best one. I put best in quotation mark because, of course, we need to define what best means. Note that model selection is more important for prediction problems than estimation problems. The idea is that in estimation problems, we are interested in the effect of a specific variable. So as long as we are out of trouble regarding consistent estimation of the coefficient related to that variable, so as long as the variable is either not endogenous and we can use OLS, or endogenous and we have to use maybe instruments or other methods, then including extra variables is not that big of a deal. In general, we include what we call control variables as a way to maybe just reduce the omitted variable bias, and it's just a way to be, it's kind of like a safety check, if you like. However, whatever model we estimate, predictions will be different. So if we care about making reliable predictions, then model selection is going to take a higher importance. If you only care about estimation problems, you just care about having a safe estimation of the coefficient of interest. Coefficients are not that important if you only care about prediction. What you care about at the end of the day is to form a prediction y hat. You don't need to know what beta hat, you don't need to be very picky about beta hats and so on, as long as the prediction is good. For this lecture, I suggest you to read chapter 6 in ISLR. They have a wide range of model selection methods. I won't go over all of them in this lecture. I'll go over the most important ones, and I will explain you the gist of them, what they entail, what is the logic behind them, why do they have a different flavor, maybe cases where one is used more than the others, and so on. So let's go over the quality of fit. We previously saw that the R-squared can be used to measure the quality of an estimated model. Now, what do you do if you have two different models with different variables? One has an R-square of 0.8 and the other one has an R-square of 0.81. At this stage, the R-square is very good. Do we need to chase the highest R-square every time? Not really. Eventually, once the R-square is good enough, we don't really care about improving it at all costs, because remember, we don't want to get to R-square of 0.99 or 0.999999. That's overfitting. So another commonly used measure is the mean squared error. So we take the square of the error, and the error is defined as the difference between the actual data and the corresponding prediction at the covariate levels. Then you take the square, because we care about the distance. We don't really care if the prediction is lower or higher. What we care is that it's close or far from the actual data. So we take the square to make it a distance, and then we average those distances over all the different predictions that we are having. So if our sample size is made of 100 observations, we're going to have 100 predictions. And so the MSE will be the average over 100 different distances. It is exactly an Euclidean distance formula. Yeah. The Euclidean distance, you would have to take the square root after that. Doesn't really matter here. In fact, some use the mean squared error and some use the root mean squared error, or MSE, which is the square root of this formula here. So it measures the distance between the data and the predictions. What's good about it is that it can be used regardless of the model. The model could be linear, in which case f hat has the combination of betas and x's that we saw in the past two lectures. It could be quadratic in the parameters or in the variables. It could be non-parametric. It is not something that we are going to cover in this course, but the idea is to use to fit the data, but not using a straight line or parabola and so on and so forth. Rather, the idea is to let the data shape the regression function. Trees are something that I'm going to cover in 2 weeks in the machine learning algorithm lecture that consists in making predictions based on where observations, in which categories observations fall. So the idea is that observations are going to be categorized. They're going to be placed in one leaf or a group of other observations versus other leaves, and all the observations in one leaf will have the same prediction. And there are many other ways to build predictions. We have k nearest neighbors. We have maximum likelihood estimation. We have support vector machine. We have neural networks. You guys might have heard about something called deep learning or neural networks, which are the trendy algorithms, the trendy machine learning algorithms these days. That is something I will cover briefly. Those are other ways to build predictions. And if my f hat is equal to xi prime times beta hat, we are back to the OLS minimization problem. Plug xi prime beta here, and if you minimize this function, you obtain the OLS estimator. So the OLS estimator minimizes the in-sample mean squared errors. The population equivalent of this measure would be an expectation. It would be the expectation between a variable y and its estimator, its predictor. The sample used to estimate the model is called the training sample. The OLS estimator pretty much minimizes the training sample MSE, or the in-sample MSE, where we assume a specific form for the regression function. At the end of the day, if you care about prediction though, you don't really care about predicting things that you observe. If you observe them, you don't need to predict them. So when you make a model and you estimate a model, you want to build predictions, or you want to build a way to predict things that you do not observe. And you use what you observe as a template to predict what you will not observe. If you observe the x's but you don't observe y, then you would like to use the estimator that you used on a sample to extrapolate the results of these regressions onto unobserved data. So, minimizing the MSE of the sample we use to estimate the model does not tell much about the quality of the fit. Remember, we can add more variables and make the R-square bigger and bigger and bigger. This is overfitting. The fit of the regression is going to be great. However, it doesn't tell us if it helps us predict other data well. So let's see quickly how different models do on a data set that was not used for the estimation. So the outline of this lecture will be to talk about the bias-variance trade-off first. This is a very important part of model selection. It is in fact why we need model selection. So I'll cover the bias, then the variance. Then we'll get into the selection of linear models in particular. There have been a lot of different tools designed to select the best linear model. After that, I will go over other types of model selection that can be used for all kinds of predictors, for all kinds of methods that predict some data. Finally, I will quickly talk about model averaging as another alternative to model selection, and I'll tell you about its appealing properties. So let's start with the bias-variance trade-off. The bias of a statistical method refers to the error coming from approximating the real relationship by a simpler one. Remember that we do not know the real relationship. Sometimes we might want to know about it. Sometimes we don't need to know about it. We just want to predict things. Imagine that the real relationship is linear. Y equals xi prime beta plus some error term. Then a linear model will do great. In fact, it will be not a perfect fit, because again, it's an estimation, but it will be the most appropriate model. Chances are that if you include x squared or x to the power of 3 in such a model, the beta hats associated to those variables will be very close to 0. Simply because adding curvature, in this case, will not help us predict the data better. But in the world, are things linear? Well, rarely. So if not, a linear model will fail to pick up the true relationship patterns, will fail to pick up the curvature of the relationship. So as flexibility increases, the bias of the method decreases. What I mean by flexibility is allowing for a prediction line which is not a straight line. It is more flexible in the sense that it is allowed to go through more points instead of staying on a straight line. Any model which is a bit more complex than a linear model is more flexible. For instance, adding x squared or x3 to the regression is more flexible than just sticking to x. The more flexible the method, the more it will go through points in your data. So the bias of the method will decrease. Now, let's talk about the variance. One can show that we can always increase the fit of the training data by increasing flexibility. This is related to adding variables to a linear model. This is the same as increasing flexibility, and we saw in the previous lectures that it leads to overfitting. Our R square gets bigger and bigger, but we fit the points too closely, and that could be a problem. Why is it a problem? Because the predictions, f hat, will vary a lot if I use another training data set. If I estimate a parabola on two different data sets, even though the data might be coming from the same original random process, my parabolas might be quite different. Instead, if I use a linear model, my two straight lines might be very close to each other. So the method is going to have a low variance if it's not flexible. The more flexible the model is, the more erratic its predictions are, the more variance it has. Because if I go to another data set and I estimate I use the same method on another data set, I'm going to get another erratic behavior which doesn't look like the first erratic behavior. That's what we call the variance of a statistical method. Remember that we want something which is flexible to capture the patterns on the training data set. Because these patterns are going to repeat themselves on other data that follows the same data generating process. However, each data set is also going to have a component, a pattern of its own. This is the pattern we don't care about. This pattern is due to the error terms of that particular sample. We care about the general pattern. Is it a parabola? Is it a straight line? Is it more periodical, like a sine function? Is it like an exponential function? We do not want to pick the random patterns which are around that general pattern. So if we increase flexibility, however, we might pick up patterns which are specific to the data set we are looking at right now, but that don't repeat or don't apply to other data sets. And this is overfitting. In the case of a regression, a linear regression, flexibility can take two forms. Either I have the same x, but I am adding x squared, x3, x4, x5, and so on. And I mean powers. Or I'm adding different x's, but I'm adding more and more and more of them. Both types of flexibility will increase R squared as we increase the number of terms used in the estimation part. On the other hand, a rigid model fails to pick up the relevant patterns. In the previous lecture about linear model extensions, I talked about the first assumption, linearity. That could be a problem if the actual data doesn't look very linear. If you remember, I fit a straight line through some data that doesn't look linear at all. The straight line is almost flat, whereas the data did some kind of a shape like that. And there was a logarithm in the process. Too rigid and we cannot grab that curvature. Too flexible and we might be just picking up patterns which are specific to this data set, which do not repeat in other data sets. To sum up, not flexible models don't try hard enough. They have a low variance. The straight line will more or less be the same in any data set, which is generated from the same process. But too flexible models will be too erratic, and this erratic behavior will change a lot from data set to data set. Let's decompose the population regression equation. Y is a function of x plus some random term. You can decompose the population test mean squared error as follows. Here, I have an observation y0, which is not part of my training sample, and I have a corresponding x0. The mean squared error of this prediction can be decomposed as the variance of my estimate, my predictions, plus the bias of my predictions to the squared, plus the variance of the error term. The bias is the average of the actual true relationship and its prediction. So to obtain this formula, you can write y0 as being f of x0 plus epsilon, and then decompose the square. Note that the first term is positive, the second term is positive because it's a square, and the last term is positive as well. It is a variance. So the first term is the variance of my statistical method. Note that here I do not talk about the variance of a coefficient of beta hat. I'm talking about the variance of xi prime beta hat, if you like. The variance of my predictions. The second term is the bias elevated to the square. And the last term is what we call the irreducible error. Why irreducible? Because it is everything that we do not observe. So by design, this thing has a variance. And it is reducible in the sense that it is everything else that our main relationship is not picking up. Now, as the flexibility of a method increases, the bias, as I said, is going to decrease. F hat is going to be closer and closer to the real f, and the bias will decrease. On the other hand, if you increase the flexibility, this first term, the variance of f hat, will increase. So when one of them increases, the other one decreases. Since all the terms are positive, we want all of them to be low. We cannot just try to decrease one because it means that the other is going to be very high. So if we want all of them to be low at the same time, because we want to minimize the mean squared error, then it means there is some sort of a trade-off where they're both low at the same time. It's either very high variance, very low bias, or very low variance and very high bias, or something in the middle, where they're both relatively high or relatively low. But the idea is to both have them as low as possible at the same time. Let's apply this, let's look at how this concept is illustrated on a training data predictions. So I generated this data, which is not a linear function of y. I added some curvature on purpose, and I estimated 4 different models. The cubic model includes x, as well as x squared and x3. And you can see that the prediction line is this green line, has the curvature of a cubic function. It's like this. The linear model is an OLS. I just regressed y on x and reported the regression line. And this is the orange line. It goes through a bunch of points and it approximates the true relationship by a linear one. The third one, the purple line, is the non-parametric method. I don't want to go into detail about how to obtain that predictions. You can check my code on the RMD file later. The idea is that I made this model very flexible on purpose. It is so flexible that you can see the regression line is actually picking up not all, but many of the data points. This means that if x is equal to -1 here, my prediction is also -1. My prediction is the same as the corresponding y data. So my non-parametric method here is very flexible, which is why we have this erratic movement. And it is very good at picking up the patterns of my training data. Finally, quadratic is a parabola. I'm regressing y on x and x squared, and I get this red parabola. Another approximation to this non-linear true relationship. But as I said, we don't really care about linking the dots of the data we already observe. We would like those curves to do well on a data that I do not observe. I only observe the x's and I need to guess the y's. Well, let's take this model with the same slope coefficients. So I mean by that I'm taking the same intercept and slope of the three cubic linear and quadratic relationships. And I keep the same parameters for the non-parametric method. Non-parametric methods feature what we call tuning parameters, which are parameters we need to adjust to increase the flexibility or decrease the flexibility. Here, this model is very flexible. What if I take this exact very flexible model to another data set that I did not use to estimate those lines? The other data set, however, follows the same process as my current training data set. The relationship is exactly the same, it is just another sample. So overall, the shape maintains for those new points. Now, obviously, the non-parametric estimator is even more erratic than before, and its pattern is very different from the training dataset. If x is equal to around -1, the non-parametric estimator is predicting a value of more than 20, coming from the previous graph. If you go to the extremes, you can see here that it's even more erratic, where it goes up and down, whereas the three other functions haven't changed. They are the same parabolas, are literally the same lines. I'm literally taking the first parabola and transposing it into my new dataset and see how well it predicts. I'll do the same with my linear function. So I'm using the same slope as the one I estimated in the previous dataset. And same with the cubic and quadratic regressions. Obviously, now you can see that the green line and maybe the red line are the best at predicting the dataset at hand. Whereas the non-parametric estimator, the most flexible estimator here, is very, very erratic, and some points do not match at all, although they were nicely matching in the training dataset. Finally, the linear relationship is the same. It goes through many points. It is not as precise because, well, the true relationship is not linear, but it also seems to do fairly better than the non-parametric method. Note that this orange line here looks like it has a different slope than the previous one. The slope is exactly the same. It is just that the graph is on a different scale. You see here there is number 8, whereas here we are at number 15, which is why it looks flatter. Now, let's look at the actual MSEs for each data set and each method and see which method is doing the best in terms of predictive power. So I have two samples, the test sample and the training sample. Note that, so on the x-axis, I report flexibility with linear, quadratic, cubic, non-parametric. So from left to right, we are going higher and higher in terms of flexibility. And on the y-axis, I report the value of the MSEs I showed before. Note that the MSE of the training dataset decreases monotonically as I increase the flexibility of my statistical model. The more terms I use, the better I am at predicting the data. And this is where overfitting comes in. If I had something even more flexible than this, something more erratic, then you could imagine that this point would get even lower. Now, if I apply my estimated models on a data set of interest, like a test data set, you can see that the test data set at the beginning decreases, but then past the cubic function, once I go to the non-parametric function, it shoots off. This is because we have those erratic movements that produce pretty poor predictions. Look at the right. We are between 2.5 and 3. We have 3 points which are around 15. The corresponding predictions with my non-parametric method are between 2 and 5. And even lower. And this is the trade-off I was talking about. As you increase flexibility, you are decreasing the bias and increasing the variance. However, at the beginning, the bias decreases more than the variance increases. So when I go from linear to quadratic, overall, my test MSE is better. It is lower. That's because the variance increased less than the bias decreased. So there was a huge gain. Here the gain is coming from the bias. Then when I go from quadratic to cubic, I am adding one more term. So I am increasing flexibility again. And again, the test MSE is going down. Now, from cubic to non-parametric, which is a huge difference in terms of flexibility, you can see that now the test MSE shoots off and is way higher for the non-parametric method than for its competitors. This is a trade-off. At some point, adding an extra variable will not decrease the bias so much because you already have 100 observations. Having a 101st observation is not going to make a huge difference. However, it is going to still increase the variance of the method. So the MSE starts increasing again, and that's coming from the increase in the variance of the method. The training dataset would tell you, pick the most flexible one. Pick it. It's my smallest MSE. But when you think about the overfitting aspect of training samples, and you look at the test sample instead, the test sample is telling you, go flexible, but not too flexible. And here it says, go to cubic. Regress y on x, x squared, and x3. That will provide you the best predictions overall, on average, out of these four methods. So to summarize, the training dataset MSE, is a decreasing function of the flexibility. In words, the more flexible the model, the better predictions of the training sample. The other aspect is that the test data MSE has a U-shape, and it will always be the case because of this trade-off. In words, a very flexible model and a non-flexible model do not predict as well as a moderately flexible model. So the different selection methods I'm going to go through in this lecture aim at finding the best trade-off every time. Being aware of this trade-off, the following selection methods are going to try to incorporate this trade-off one way or another in order to find the best one. So let's start with selection among linear models. We are going to cover many different methods. First of all, we'll cover information criteria. Those are formulas that include both the fact that the bias decreases with flexibility, but the variance increases, and vice versa. Then I'll go to subset selection, which consists in choosing the optimal subset of variables. Which combination of x's should I include when I make my predictions? This includes best subset selection and stepwise selection. Then I'll talk about shrinkage methods. Two in particular, the ridge regression first, and the lasso regression second. Then I'll talk about dimension reduction methods, which consist in not choosing the best combination of variables, like all the methods proposed above, but rather reduce the dimensionality of the data so that I'm not falling for a very high variance in the method. That includes principal component analysis. It might be familiar for some of you guys. It is used extensively in statistics. Partial least squares has a similar flavor, but it acts in a supervised way. And as I mentioned, many more. I will refer you to chapter 6 of ISLR for the other ones. But these ones will give you the main gist, the main ideas about how to select the best bias variance trade-off. So let's get into information criteria. For linear models with different number of variables, we can use some sort of criteria that account for the bias variance trade-off using the training sample only. We don't need to check how this is working on another sample. The formula will already include the fact that too flexible is not good, too rigid is not good either. Let's define RSS as the residual sum of squares of the training sample. So I take my data, y, minus my predictions, I take the square, and I sum them up. Note that if I multiply everything by 1 over n, I go back to my mean in sample mean squared error formula. We call it residual because it is everything that is not explained by our model. Data minus prediction, whatever is left is a residual. Now, remember that the variance of the error term typically is assumed to be some number sigma squared. If we are in the case of homoscedastic errors, then this number is constant across observations and across x's. Imagine we can estimate it consistently, which we already know how to do from the 2 previous lectures. We are going to use this as a proxy for the variance of the model. Given that the residual sum of squares decreases as the number of variables increases, one should include some sort of penalty. This formula alone will not account for the trade-off. This formula is just pretty much an in-sample MSE. And we saw that in-sample MSE is good when you want to make training sample predictions, but we never want to make training sample predictions. So here, we are going to include a penalty term to account for the fact that increasing flexibility will become bad. There are 4 different criteria for this in this lecture. There are many more in real life. Those are the most common ones. The first one is called Mallow's CP criterion. Mallows is a researcher who provided this contribution with a coefficient called P, which is defined as 1 over n times the residual sum of squares plus 2 times d sigma hat squared. D is the number of variables that the estimated model contains. So the second term is increasing when d increases. We already knew that the first term decreases when d increases. So we made the penalty term so that it increases when d increases. If you want to minimize this criterion, then you need to take into account the fact that you are adding 2 things which are positive. So you might want to mitigate both at the same time. Another criterion is called the Akaike information criterion. Akaike is a famous Japanese statistician who came up with the following formula: 1 over n times sigma hat squared times RSS plus 2d sigma hat squared. It is exactly the same as the previous criterion, but the 1 over n at the front is replaced by 1 over n sigma hat squared. Note, the AIC is used if the error term is assumed to follow a normal distribution. In this case, it would be equivalent to CP. If you do not assume a normal distribution, then that criterion might not be as accurate in choosing the best model. The Bayesian information criterion, BIC, is defined as 1 over n sigma hat squared again, same as AIC, but the second term in the brackets is what's going to change. Now, we have a log of n, and there should be a d somewhere, I need to add it later, instead of a 2. The idea is that the penalty now is also going to depend on the size of the sample size. Because the second terms are not exactly the same, AIC might or will, in general, choose a different model than BIC. Which one is better? There is no clear-cut answer. In general, it is good to look at both, and there are a fair number of other ones. It is good to look at them and to look at which method reaches consistently a low criterion number. A model who has a low AIC and a low BIC at the same time would be preferred to a model who has a very low AIC but a high BIC, or vice versa. So the weight of the second term is such that the models will choose a different model. The criteria will choose a different model. Finally, the adjusted R-square is defined as 1 minus, and instead of just being RSS, residual sum of squares, over total sum of squares, each side of the fraction is divided by a number involving the sample size and the number of covariates. So this adjusted R-square, because of the D, now includes the overfitting feature, or rather it excludes it. Originally the R-square could be increased by adding more term or by being more flexible. This adjusted R-square is going to mitigate that effect by also taking into account the number of variables that are being used to estimate the models. Any questions? Okay. Why don't we take a break and resume at 3:30, which is in 12 minutes. And then we'll talk about subset selection. Okay, let's resume the lecture and let's talk about subset selection now. Here I am. So, when one has many covariates available, the question is not only to know how many variables to include, but then which to include, which combination. Do we want x1, x2, and x3, or do we want x1, x2, and x5, x3, x4, and x14, and so on? If one has access to 5 covariates, think about how many models it makes. It makes one model with 0 covariates, which is just an intercept, and in this case, the prediction is actually the average of the y's, y bar. There's going to be 5 different models with 1 covariate, each of them alone. Then 10 models with 2 covariates, where you pick 2 covariates out of 5. So there's going to be 10 different models with featuring 2 covariates. There's going to be 10 models with 3 covariates as well. That's a typo here. 5 models with 4 covariates. You can choose these 4, then these 4, then these 4, then these 4, then these 4. There's only 5 different combinations of 4 variables. And finally, there is only one model that has 5 covariates. The full model, the complete model. So imagine that now you have 10 covariates. Think about how many models it is going to make. One can reduce the dimension of the problem by doing the following computations. Find the best model for each number of covariates. So you find the best model with 1 covariate, the best model with 2, and so on, based on the best R-square every time. So you might have different models of 2 covariates competing, but you choose the best one based on the R-squared. Then, once you have the best 2 covariate models, the best 5 covariates model, and so on, you find the best model overall based on one of the 4 criteria we saw in the previous slide. So, if you want to choose between 2 models with the same covariates, choose based on the R-square. Now, the R-square is always going to be higher with more covariates. But because we want to avoid overfitting, we should not choose our model overall based on R-square. So once the first step is done, we look at different criteria like AIC or BIC or CP or adjusted R-square in order to choose the ideal number of covariates. So the first step consists in finding the best combination of each number of covariates. Best combination when I use 1 covariate. Best combination when I use 2 covariates. Best combination when I use 3, and so on. The second step consists in, among all of these best combinations of 2 versus 3 versus 4 versus 5 variables, I choose the best number of variables based on another criterion than R-squared, because remember, the R-square will always select the model with more variables. So you will have to program some sort of a loop that is going to estimate all the possible models, choose the best combination of 3, the best combination of 4, the best combination of 5, and so on. And once you have these best combinations, overall find the best number of covariates by looking at one of the 4 criteria shown above. But as you can guess, if you have many covariates, best subset selection will become computationally inefficient. You have so many different models to estimate that it's going to take a very long time. Instead, there is what we call a forward stepwise selection or a backward stepwise selection. This is another way to select the best subset of variables. What you can do is gradually increase the number of covariates to add. This is what we call stepwise forward selection. Here is the algorithm. You start with the smallest model, no covariates. Then you choose the next variable to add based on the highest increase in R-square. So from 0 to 1, you try with this one, with the first one, with another one, with a third one, with a fourth one, and you look at what variable increases your R-square the most. This is the one you pick, and that becomes your model of one variable. Now, you're going to do the same thing for the second variable. You're going to go to the second variable and say which one increases the R-square the most. Then at the end, you choose the best model overall, again based on the 4 criteria shown above. So you're going to have the best one selection, the best one covariate model, the best 2 covariates model, the best 3 covariates model, the best 4 covariates model, and then you look at the optimal number of variables by using the 4 criteria seen above. The difference with the previous method is that here, because I select my variables gradually, I do not need to estimate all the possible models. Once I choose my first variable, then that variable will not show up again. So I don't need to estimate. Once I estimate the best model with 3 variables, I will already be including the 2 variables from the previous stage. So I will not be looking at all the possible combinations of 3 variables. It's going to be all the possible combinations of 3 variables that include the 2 selected in the step before. So less models will be estimated. It should save some time. Stepwise backward is going to work the opposite way. Instead of starting with a small model and increasing gradually, you're going to start with a very big model, in fact the full model, and little by little you're going to remove one variable. You remove one variable based on the highest R-square remaining. So let's say that you have a model with 5 variables. You start with your model of 5 variables, full model, and then you look at which one to remove first. So you're going to try, what if I remove this one? I obtain one model of 4 variables and I look at the R-squared. Okay, what if I remove this one instead? So I put the first one back into the model and I remove the second one and I look at the R-squared, and so on and so forth. I pick the combination of 4 variables that gives me the highest R-squared. Once I have my model with 4 variables, what is the next one to drop? And among my 4, I will go over each of them again, remove them, and see which model keeps the highest R-squared. Once I'm done with this, I will have one model with 5 variables, the best model with 4, the best model with 3, the best model with 2, the best model with 1, and I choose the best model overall based on AIC, BIC, CP, or adjusted R-squared. So those stepwise selection methods are a more efficient way to select the best subset of variables. Efficient in the sense that the computer will have to do less computations. If you're dealing with a very high dimensional data set with many observations and many variables, even this method is going to take a very, very long time. But at least it's going to be more efficient than using straightforward best subset selection, the best subset selection method. Any questions about these model selection methods? Okay. Another whole part of model selection is called shrinkage methods. These methods are very, very popular for many different reasons, and they are used a lot to this day when you want to select the best linear model for predictions. So the idea of shrinkage methods is you estimate the full linear model, so you include all the variables that you want, but you're going to add a constraint to your minimization problem. So think about doing an OLS, but after the sum of square residuals that you are minimizing, you add another term which is going to constrain the value of the coefficients. It is going to put a constraint on the value of the beta hats. The idea of shrinking the estimates is to significantly decrease the variance in the predictions. So we talk about shrinkage because we are going to shrink the values of the coefficients because we put a constraint on their value. We also call this a regularization method. Any method that involves a main minimization problem plus a penalty plus an additional term is called a regularization method. We are regularizing the fact that our model otherwise could yield all sorts of results. And in this category, we distinguish two different types of regression. The first one is called ridge regression. It constrains the sum of the squares of the coefficient estimates. So it estimates a linear model, but in the minimization problem, it adds this component here, where the sum of the beta squared should not be too high. Without this, the beta hats could be anything. They could be equal to 1 billion. Why not? This method is constraining their values overall as a sum to not be too high. Lambda here is coming from the fact that we are including a constraint. It is called a penalty term. A penalty parameter. The penalty term is this whole thing. And it will tell whether the constraint is going to have a big impact on your problem or not. Imagine that lambda is exactly equal to 0. Well, if it's equal to 0, this constraint here has no impact on your minimization problem, and you're back to the OLS estimator. If on the other hand lambda is very high, since you want to minimize this whole expression and your lambda is very high, then the computer, the algorithm, will want to make this quantity, the sum of beta squared, very low, to counteract the fact that lambda is high. And so the value of lambda will mitigate or not the importance of this penalty term. In the process, ridge regression will set some beta hats to low values, but never to 0. It is a consequence of the way the function looks like. So you're going to have a full model with many variables, but each of the coefficients, the beta hats, will be very small. Not all of them, but many of them will be very small. They won't be equal to 0, but they are very small. Because they're not zero, the predictions are going to be okay, no problem with this, but how do you interpret the model? You might include junk variables, which are not actually useful in terms of causality, yet their beta hat will not be equal to 0. It will be equal to something very small for the purpose of the minimization problem, but it won't be equal to 0. It is kind of hard to interpret. Predictions are going to be better, sure, but if you also care about interpreting the value of the coefficients and their impact on the dependent variable, then ridge regression might not be what you want to go with. Note that lambda should also be found. Lambda is not part of the minimization process. The minimization only happens for beta. Lambda can be found use a method called cross-validation. This is something I'm going to go over in a couple slides, so bear with me. The idea is that we're going to use another process to find the optimal lambda. The idea is you choose a grid of values for lambda. You set lambda equal to 0, 1, 2, 3, 4, 5, let's say all the way to 10, for instance. When lambda is equal to 0, you estimate the model. That gives you an OLS. When lambda is equal to 1, you estimate the model again. When lambda is equal to 2, you estimate the model again for each value of lambda. And then you use a criterion to find the best lambda. The cross-validated error, I'm going to get into it, is a proxy for the test MSE. It is another way to measure test MSE using different samples. At the end of the day, you choose the value of lambda that yields the lowest cross-validated error. Once you find your lambda, you put it back in your model here, and you look at the corresponding coefficients beta hats. That's the end of your model. You get your predictions, and you can get interpretation if you want. Now, this is kind of a drawback. The fact that we lose model interpretation by shrinking the value of the coefficients, but not setting them to 0. If you set them to 0, then it is the same thing as subset selection. If you have 20 variables in your regression, but for 15 of them, the beta hat is exactly equal to 0, then your best model has 5 variables. The 5 variables for which the coefficient is, the estimated coefficient, is not equal to 0. So sometimes we might prefer the lasso method to ridge regression method. Lasso stands for least absolute shrinkage and selection operator. LASSO. The idea is the same, but the constraint is going to look different. Instead of looking at the sum of the square of the coefficients, we are going to look at the sum of the absolute value of the coefficients. Replacing the square by an absolute value will have a major difference in that the lasso estimator sets some coefficients to exactly 0. So the second part of lasso, selection operator, occurs. It's going to shrink most coefficients, and in the process, some of them are going to be exactly equal to 0. So it's also going to select variables. Again, lambda is a penalty term. If the sum of the absolute values is high, the overall quantity is high. So if lambda is high, then we want to make the sum of the absolute values of the coefficients as small as possible. Again, if lambda is exactly equal to 0, forget about the second term and you're back to the OLS minimization problem. How should we choose lambda? It is the exact same as before. We use cross-validation. Make a grid of values for lambda, 1, 2, 3, 4, 5, 6, all the way to 10 or 20. Do your lasso regression for each value of lambda. And then look at the value of lambda that yields the lowest cross-validated error. And that's going to be the next selection model tool. In practice, neither ridge nor lasso dominate the other. It's not that the absolute value here is always better than the square and vice versa. It really depends on the data, the relationship between the variables, and it's not something that we can usually detect. There are specific cases where we can tell one is going to do better than the other, but those are very case specific. So in general, I suggest you to try as many as possible. Try both. Why not? You could say, this one produces these predictions. This one produces these predictions. What you could do as well is maybe see how both of these methods, both of these predictions do on a test data set. And you can compute the test MSE. And then you can decide whether you're going to follow a lasso versus a ridge regression for your results. Lasso has the appealing property that it selects variables in the process. So at least you won't get questions such as, how come this variable has an impact, like a positive impact or negative impact on Y? I don't have a story to justify this causal relationship. It is just a consequence of the minimization problem. So at least when lasso sets them to 0, you won't have this interpretability issue. Any questions about shrinkage methods? They're used a lot when you have to deal with many variables. In fact, there is a paper from 2012 that consisted in using a two-stage least squares estimator. Remember the previous lecture? When the variable is endogenous, you need to find instruments, and you need to perform a first stage regression where you build predictions of your endogenous variables. Since the first stage is a prediction problem, then we can apply all the tools from this lecture. And this paper in particular says, imagine we have access to many instruments. It's very rare in practice, but what if we do have access to that many instruments? The number of variables I'm using in the first stage is going to affect my predictions, and my predictions is going to affect my second stage when I do the second regression, the main one. So in their paper, they develop a criterion to choose the number of variables in the first stage so as to improve the properties of beta hat in the second stage. And they propose in particular to use the lasso method. They say if you have many variables, too many variables is not good. Your prediction is going to be too close to the actual data. If the prediction is too close in the problem I am talking about, then the predictions are going to be endogenous as well. You don't want that. You don't want them to be endogenous. That's the point of using a prediction of X instead of X. So by using less variables, you might be able to reduce the endogeneity problem, reduce the bias, but at the same time, you're going to increase the variance. If you increase the bias somewhere, you're going to decrease the variance somewhere else. It is always, there is a balance between the two. So they propose to use the lasso in a specific way and show that the performances of the final two-stage least squares estimates are satisfactory, or at least more satisfactory than the current methods. Okay, now let's move on to dimension reduction. We are still in the linear model selection. We want to select the best linear model. Dimension reduction is going to have a very different flavor, a very different thought process than the methods we saw so far. Information criteria are used to select variables. Which combination is the best? Which number is the best? Best subset is also a way to select the best variables. Shrinkage methods either lower the value of the coefficients to increase the prediction and decrease the variance of the method, or in the case of the lasso, they actually select the best variable. Dimension reduction consists in looking at a very high dimensional data set with many variables and expressing them by less variables. So this approach consists in representing many variables by transforming them into a set of variables with similar feature, but in a lesser number. So somehow I want to summarize my 100 x's into a set of 20. Once you have your set of 20, you estimate your model using the transformed variables. Now, obviously, I cannot just turn 100 variables into 20 by magic. When I say represent, I mean that I'm going to lose some features on the way, but those are features that I will not care too much about. I want my 20 variables to summarize the main features of my hundreds. But because there are less of them, I will not get into overfitting. In these methods, I will talk about two of them in particular, the principal component regression and partial least squares regression. So let's start with principal components regression. Principal components analysis, or PCA, is what we call an unsupervised learning method. I already talked about supervised versus unsupervised learning. Unsupervised means that we are not looking at a variable y, but rather we are only looking at relationship between the x's. It is used extensively in statistics because it can be used to observe high dimensional data. We can summarize those high dimensional data with a certain number of features that we can actually plot on a graph. And this will give us some ideas about what are the main sources of variance, the main sources of correlations, and so on and so forth. So it is usually used as an observatory tool, something you use as soon as you get the data, before starting any sort of regression. When you get your data, you observe some kind of basic statistics, the mean, the variance, the standard deviation, the absolute, the highest value, the minimum, the maximum, the quantiles, and so on. You might want to plot the distribution of your variables as well if you want to. It's only after checking that everything is correct or expected, because sometimes things are not reported well. You might get some NAs somewhere in your data set. You might get some numbers that don't make sense, like negative amounts for money or quantities and so on. That could be due to reporting errors, or it could be a consequence of the methodology. That is also why when you want to get a data set, always download the codebook that comes with it. So the codebook is not always there for every data set. It's a set of instructions. It's kind of a README file that says, here are the variables. Those are the names. This is how we gather them. This is, and all of those different things. Oh, we coded a variable -1 versus 1. Why? -1 means this, 1 means that, and so on and so forth. So it's usually something we use to observe data before getting into the further analysis, before getting our hands dirty. Mostly what it does, it summarizes variance and correlation patterns of covariates in a more compact way. Correlation and variance are the most important features when it comes to linear regression. In fact, if you go back to the previous lectures, we saw that the OLS formula involves the variance of y and the covariance between x and y, and the variance of x, sorry. Using principal component analysis can help us summarizing the variance of 100 variables into maybe 20 variables with a minimum amount of information loss. So we won't lose a lot of information, however, the dimension is going to be tremendously reduced, which will avoid overfitting. Here is the idea. With p variables at hand, imagine you have p variables. I was talking about 100 until now. PCA is going to look for m variables way lower than p, which is why we have two inferior signs. Those variables are going to be called Zm, that capture the main features, in particular in terms of variance and correlation of the original variables. So one variable Zm is going to be a linear combination of all of my x's. Look, my x's go from 1 to p. One variable Zm, and I have big M of these variables. One variable is going to be a linear combination of all of my x's, and the numbers in front of the x's, which is phi, will be specific to that variable m. So the idea is that if I want to summarize my 100 variables into a set of 20, big M is equal to 20, and let's say Z1, my first variable, is going to be a linear combination of my 100 x's. But it's only a combination, it's a sum. So at the end of the day, it's a sum of 100 terms all into one term. The way those phi's are found, or not really estimated but found, follows an algorithm that I don't want to expose you to today. But the idea is that each z is going to be a combination of the x's. So my 20 z's will gather the main variance and correlation patterns as my 100 x's. And when I say main, I mean 95% of the variance and the correlation are pretty much the same, the variance and correlation patterns. But I have 5 times less variables. So PCA is going to find the coefficients, phi jm. There's going to be a coefficient for each x and for each z. Once you find these 20 z's, then you can use the 20 z's in your regression. How many m's should we find? Why 20 and not 21 and not 22? Well, guess what? Cross-validation. I will talk about this very soon. It is a very, very important concept that is used tremendously, extensively in the machine learning literature. In fact, it's probably the most used tool in machine learning. It can apply to other models which are not linear, which is why I'm going to talk about it later. Note that these z's, being combinations of different variables like age, number of kids, income, social status, and so on, those z's don't really have any interpretation. They don't really have a meaning. So if you want to regress y on your z's instead of your x's, the quality of the prediction is going to be better, but you won't have any interpretation. If z1 increases by 1 unit, it doesn't mean much because z is a combination of x's and each x could be expressed in a different unit. So be careful. You don't want to use PCA. You don't want to regress y on z if z doesn't mean anything. Z is a combination. It's like an index. It doesn't tell you anything about what if I have one more kid? How is it going to affect my earnings? What if I have one more year of school? No. If z increases by 1, it could be the result of many different things inside increasing by a little number. So again, it is a tool used for prediction, a way to reduce overfitting. Partial least squares has a very similar flavor. So while PCA is unsupervised, it only looks at the x's together. We didn't even use y in the first place to find our z's. Partial least squares is supervised. So to find those combinations of z's, to summarize the data the best, we are going to involve y as well. The idea is that since y and x are correlated, when I build my z's should also result from some sort of correlation with y. So y should play a role. The idea is exactly the same as before. My z is going to be a linear combination of my x's, but my phi's are going to be using y to be found. So PLS, partial least squares, uses y in the process of finding the phi's in such a way that the z's, my 20 z's, will also not only will summarize my x's well, but will also keep some correlation patterns with y. If I want to use z's to replace x, I should expect my z's to also have some causation power, to have some correlation with y, right? So y is included in the process to find those weights phi. The second stage is exactly the same. You regress y on your z's and you can build your predictions. But again, you don't have any interpretation here. Increasing z by 1 unit doesn't mean anything. It is a pure prediction variable selection tool. Any questions? Okay, so now let's move on to the more general approach, which does not only look at linear models, but rather look at any type of predictive model. Any model that consists in predicting a variable y, could be linear, could be some fancy machine learning algorithm we're going to study soon, and so on, can use these methods: validation sets and cross-validation. So the methods above apply to linear models because the flexibility of a linear model is dictated by the number of variables included, 3 versus 4 versus 5. That's what flexibility means when you look at a linear model. So, this is why the information criteria include the number of variables, because we know that this is what is going to drive the variance of the method up and lower the bias. This is why shrinkage methods and best subset selection methods are selecting the number of variables, and inside the number also selecting the best combination. Validation sets and cross-validation work on a broader range of statistical methods, as they are just based on prediction. Whatever way you predicted your, whatever the way you are predicting future data or any data, validation sets and cross-validation can apply. So that's why they are widely used in the machine learning community, where prediction is usually the main focus. As mentioned before, we want a model based on out-of-sample performance. We don't care about doing too good in the training sample. If we do too good in the training sample, we are overfitting, and we want to avoid that. So, we should somehow assess out-of-sample performance one way or another. This is not something we did so far. So far, we only had one sample, the training sample, and we were using formulas that were taking into account the fact that overfitting was likely. Now, we are going to explicitly avoid overfitting because we are not going to look at how we predict the training sample, rather how we predict another sample, the out-of-sample performance. It's often called OOB, out of bag, or OOS, out of sample performance. Validation sets work the following way. You have one sample, you cut it in two parts. Equal size, 1/3, 2/3, anything so that you have a relatively good sample size in each. If you only have a sample of 100 observations, you might want to go with 50-50 or something like that. But if you start doing 25-75, well, the model with 75 observations will not do too bad, but the model with 25 will likely to overfit very, very fast. The training data set is going to be the first data set. That's the one I use to estimate the model. I make my OLS coefficients and so on and so forth, like what I showed at the beginning of the lecture. The test dataset is used to test the model, the different models' predictions. This is why I called the previous datasets test dataset in the graphs I showed you. I was trying to give you an appetizer of what the validation set approach is. The best model is chosen based on the lowest test MSE. So, what we're doing is, I use my training sample to find my OLS coefficients and find the best straight line, or the best parabola, or the best cubic line, or the best quartic, which is to the power of 4, and so on. Or I use this training sample to make my best regression tree, and any other non-parametric fancy methods you might be aware of. But then, I transpose those predictions and try to predict the test dataset. And as I showed you in the previous graphs, the test data MSE is going to have a U shape because of the bias-variance trade-off. And then you can select the model that features the lowest test MSE. Let's look at an illustration in RStudio. There's a data set called credit that comes from the ISLR library. So, among other variables, it reports the balance, which is the average credit card debt. It is not lower than 0 here. It's either 0 or positive. We observe other variables, such as quantitative predictors, like age, education, income, qualitative predictors as well, gender, is the person a student status, marital status, single, married, widowed, divorced, and ethnicity. What we want to do here is predict the balance of a customer based on what we observe of him or her. We observe the age, the education, the income, the gender, the student status, the marital status, and the ethnicity. And there are a couple more variables as well. In order to predict balance, what combination of variables to include? I'm going to take here linear models only, but I'm going to use the validation sets approach to show you how the selection is being done. So the process goes as follows. Divide the dataset into 2 datasets. Cut it in half. What I did here is I divided in 3 because the first one is going to be the training, the second one is going to be the test, and the third one is just going to be, well, imagine I have only the x's of my third. Obtain predictions for the corresponding balance, and I can compare with my third data set. But in general, it's going to be just 2. So, first of all, train or estimate all the possible models on the training data set. So I have many possible combinations of variables. I'm going to estimate all of them. All the models with 1, all the models with 2, all the models with 3, and so on. Then I take the predictions of each model and I apply them to my test data set. I can then compute the test error or the test MSE by looking at the test data set data and taking the difference between this number, these numbers, and the predictions. I take the square to get a distance and I compute the average error. We also call this the mean squared forecast error, MSFE. That's another term that you might encounter if you read some literature about it. Finally, you choose the model with the lowest test mean squared error. The approach is fairly simple. It's really, I estimate my straight line, all of my straight lines, and then I take the first straight line to the other data set, see how that straight line does. Then I take my second straight line, take it to the other data set, see how my second straight line does, and so on. And I compare the best, I look at the best straight line based on that second sample. You can take a look at my R markdown file for many different with a lot of code. This could be useful for you guys later if you're interested. You can use my code anytime, no problem with that. I commented it as much as I could, but sometimes it might look obscure. Feel free to ask me and I can tell you what I did. You can copy paste this code for any future analysis you want to make, no problem. Basically, the process yields the following graph. This is the graph where you want to get at the end. On the x-axis is reported the number of variables. So I have different models with different number of variables. I have a model with 3 variables. That would be, is that a 3? Yeah. I have 1, 2, 3, 4, 5, 6 model with 4 variables, and so on and so forth. And with all of these different models, which are different combinations, I took the predictions to the test dataset and I compute the test error or the test MSE. And I reported those values on this graph. So you can see that for each number of variables, here for instance 5 variables, I have a bunch of test error, test MSE. I have the same for 6, for 7, and so on and so forth. Finally, I want to find the lowest point. I want to find the lowest test error. So here, I highlighted in red the best model in each category. So this point here is the best model with 5 variables. The test error is something like 9,300 or something. 9,275. Then here I have the best, all the models with 6 variables, and the best one has a mean squared error in the test dataset of 9,250, and so on. By doing this, I now see the best 1 variable model, the best 2 variables model, the best 3 variables model, and so on. I cropped the results, but there is also here a 1 variable up there, but the test MSE is way higher. And I have the same here with more. Finally, I can find the best model. The best model is going to be where my test error is the lowest. It is going to be here. It looks like 6 variables, 1 model with 6 variables here. I don't know which one yet. There are many models with 6 variables. But the lowest test error is achieved with a model of 6 variables. And again, you can see the U-shape. Decreasing, 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 because flexibility increases, bias decreases. Bias decreases more than variance increases. And then after some point, the variance increases again because of the crazy erratic predictions. And the test error increases again. Now, the hardest part here is that I have many models, and each of them corresponds to a specific combination of variables. So I know that 6 variables is going to be the best model, but which 6? I showed you 8. There are many combinations of 6 variables I can make out of 8 possible variables. Or 10 variables actually, there are more. So then I have to use another piece of code to see among all the possible models, I have to find where was the test error found. So I can align pretty much my test error, my test MSE, with each model. I can say age income, test error, age income ethnicity, test error, test error, and so on. Then I find the minimum, which is what I did here. I said for each number of variables, 1 versus 2 versus 3, I want to know I want to know the lowest MSE. So that's what is highlighted in red. Now I need to retrieve the best 6 variables model. So I can go back to my data, which says test error, income, and age. Test error, income, age, ethnicity, and so on. And I can look for which point had the lowest MSE. R is going to tell me, oh, I found the lowest test MSE at row 180. I think this is something like that in this precise example. Then you look at row 180 and it will give you the formula. It will give you what variables were included. This is the best model. In my code, I called it best combi for best combination. So I generated a formula. I made this function to obtain this formula, with the tilde, y tilde x1, x2, x3. I used it to assemble all the best variables. I used credit 3, so I used the third data set here to see how that best formula is doing on an external data set. It seems that the best variables are income, limit, that might be the limit on the credit limit that is allowed for each individual that they can report. Cards, I believe, is the number of credit cards they own, age, education, and whether the individual is a student or not. In North America, you know that students are poor and often in huge amounts of debt. So it is not surprising that student status helps us predict the credit card balance of an individual. And here it says that student yes, which means that if a student is, if an individual is a student, being a student versus not being a student leads to an increase, leads to a higher credit card debt of around 403, I believe it's dollars in the data. Just being a student, the prediction is that you just have $400 more of debt. Note that the multiple R squared is pretty big, 0.95, and the adjusted R squared, which is the one I talked about previously, is a bit lower. The idea is that it's a bit lower because it mitigates the takes into account the number of variables that are being used. Since there is 6 variables and the data set is not that big, I believe it's, well, 127 degrees of freedom. So we have 133 observations in this data set, which is a third of my original data set. Let's look at the difference. Well, let's look at the plot of the balance, the actual balance of the observations in this data set and the predictions created by this model. Note that here I am not just taking my predictions from the first model, applying them to the third data set. I use the training and the test samples just to figure out what is the best formula. Now, give me a new data set. I'm going to rerun the model. I'm going to re-estimate the model using my new data set. So this is more or less the 45-degree line. You can see that here we have 500, 500, 100, 100, 1000, 1000. So the 45-degree line here is a way to see that, well, along the 45-degree line, prediction is equal to data. X equals Y. That's the definition of a 45-degree line. And here you can see that our predictions are fairly close to the 45-degree line for most of the points. So the predictions are pretty good. But the selection of these variables came from another data set. It came from my training data set and my test data sets. There are a couple of observations here which are not super well predicted. Those are the ones at the limit, at the border, the ones who reported no credit card debt. Now, I talked about validation sets, and I told you about cross-validation. Cross-validation is a very similar approach. So the sample is cut, but not just into training and test once. It won't be done once. That's what I wanted to say. So, first of all, take your full data set and divide it into K groups. One group is called a fold. K usually is a rule of thumb. Imagine you can divide it in 10. The idea is that you want each of your smaller samples to still have a reasonable amount of observations. If you only have 100 observations in your data, you don't want to divide it into 10 separate small data sets because each of them only has 10 observations. But if you have 10,000, you can divide it in 10. Each data set is going to have, each fold is going to have 1,000 observations. More than enough to be accurate most of the time. Now, take the first fold, your first subset, and put it aside. Now take your 9 other folds, your other folds, put them together now. So you're going to get a rather big portion of your total sample. Train the model, so estimate all the models, and use the first fold that you put aside as your test data set. So far, you use the validation set approach, but instead of being half-half, test and data, it's test and training. Training is going to be rather big, and test is going to be a rather small fraction of that sample. But so far, same thing. You can compute the test MSE on that first group, that first fold, and you get one test MSE. Now, repeat that, but instead of putting the first fold apart, you take the second fold out, and this is going to become your new test dataset. Again, all the other ones, put them together, train your models, test the models on that second fold, and you get one more test MSE. So there was the first one from putting the first fold apart. Now we have a second one. Now repeat this as many times as you have folds. Third fold aside, fourth fold aside, fifth fold aside, and so on. So of course in the process, the training samples will have a certain amount of observations which are exactly the same. In the first part, I used at my training the second fold, third fold, fourth, fifth, all the way to 10th together. In the second step, when I take the second fold out, now I'm using the first fold as a training, but it was used as a test just before. And I'm using third, fourth, fifth again as training. So you're going to do this k times because you have k folds. And so you're going to get k test MSE. So each model of that many variables is going to have k test MSE. To find the best model, take the average of those k test MSEs. So instead of relying on only one test MSE, like we do in the validation sets approach, we're going to take an average of test MSEs. Okay? When you have a high amount of observations, then cutting your data into folds will not be a big deal because each of the folds is going to have a high number of observations still. But by being able to obtain different test data sets every time, it's like repeating the validation set approach many times. To take another average on top, so this is going to be the average of k different test MSEs. If you have k folds, it's going to be 10 folds. It's going to be 10 test MSEs. And this is another way to select the best model. Note again that it doesn't have to be number of variables. It could be the best tree. It could be the best non-parametric model I talked about at the beginning. I won't give you the details of that non-parametric estimator, but the idea is that you can see how erratic it can get. In fact, there is even a special case of cross-validation called leave one out cross-validation. As the name suggests, instead of taking one fold out, you take one observation out. So if your sample has 1,000 observations, you take one observation out as your test observation, and you keep the remaining 999 as your training observations. You run your models on the 999, and you try to predict the last one, the one that was left out, and that gives you one test MSE, one test error. Then what you do is you take the second observation out, and you put the first observation back in, and you do the same process. So instead of having k different test MSEs, you're going to have n different test MSEs. for observation 1, for observation 2, for observation 3, and so on. And you can take the average distance again. It is more time consuming, as you can assume, because if you have to make a loop and estimate all the possible models that many times, even with nowadays computing power, it can take some time depending on your data set. Any questions? R has plenty of routines which can already do which can do this already. So n is k minus 1. No, it would be n minus 1. Because you want to divide your data into n groups in this case, if it's leave one out. Or are you talking about leave one out? Or are you talking about just k-fold? It depends what you mean. K is not the sample size. K is not the sample size. K is the number of samples I am making. I have my big sample. I'm taking blocks. And I'm taking K different blocks. I keep one block as my test, and I take all the other blocks together as my training data set. But then I can do this by putting the first fold back in and take another fold out. And I repeat the process until each fold has been put out. So leave one out cross-validation is the same as n-fold cross-validation. I divide my sample into n samples. So I take one observation here, one observation there, one observation there. I take one out, put all these ones together. First one. Then I take that one out and I put all the other ones together. And so on. R, as I was saying, R has many routines that do cross-validation for you. And you can specify how many folds you want. In general, the default option is 10. It is a rule of thumb because there are no, we can always figure out what K is now. But we are already using cross-validation to select the best model. So if you, on top of this, have to find the best K, then you're getting into a rabbit hole of estimating a tuning parameter, to estimate the tuning parameter, to estimate the tuning parameter. K is taken as 10 as a rule of thumb, but you can always try with 10 versus 11 versus 15 and see how it affects the actual mean squared errors of your test datasets at the end of the day. And in the case where K is equal to 2, well, you have one training data, one test data. That's pretty much the idea, more or less, because you have to do it twice. You would swap. It is a very powerful method because it uses the data at hand to do as if we had more data than what we have. It is very powerful. By taking those chunks and assembling those samples differently, it is the same as obtaining a new sample. Of course, some observations are going to repeat themselves, but overall, they will not repeat themselves all the way. And so, from one sample, you're kind of generating many different smaller samples that will help you select the best models, but not based on one sample, based on K kind of samples. But those K samples are coming from one big sample in the first place. It's hard for me to explain, but there is a magic side to it. There is only so much you can do with the sample, but apparently, when you take chunks and reassemble them together, you can actually improve the performances of your statistical methods. cross-validation is very important for you guys to know, especially once we'll get into the machine learning algorithms per se, how to predict with machine learning. Let me finish the lecture with model averaging. Model selection is important if one cares about estimating coefficients. You want one model over another, which variables are the relevant ones. But if you only want to predict well, why do you want to include that variable versus another? Whatever predicts well, and that's what you're going with. Best test error, for instance. So model averaging is ignoring model selection. Instead of choosing one model, why don't we compute all the different predictions for different models and take the average of these predictions? It turns out, theoretically, that taking averages is always better than not. Why? Because you are keeping the same bias of your statistical method, but the variance of your statistical method is going to dramatically decrease. By averaging predictions over different models, your predictions become more stable. The bias, though, is unchanged. It's not better or worse. However, the variance is lower. So instead of choosing one model and going through a long process of I want this one with these variables and so on, you can say, no, I'm going to estimate all of them and I'm going to take an average. It shows better predictive performances than a single model. Machine learning algorithms in general focus on prediction, so model averaging is used quite a lot. Have you guys ever heard of the Netflix competition? In 2005 or 6, apparently Netflix was already around. Surprisingly, I thought it was more recent than this, younger. Netflix was in 2006, maybe 2007 or 8. You can type it online. It's well documented on Wikipedia, for instance. Netflix released a data set of movie ratings on their platform, TV shows and movies, maybe just movie ratings. And the challenge was predict the probability of a movie rating or the probability of watching a movie by a user better than our Netflix algorithm. So pretty much Netflix challenged people to provide a better predictor of preferences than their own. And I think the reward was $1 million. I think that's what it was. It turns out many models, many teams actually did better than Netflix algorithms. And many teams used model averaging. In particular, the winners had some sort of model averaging. So they use all kinds of different models. And I don't think they use linear models because they don't need to specify a linear relationship. They just want to predict. So Netflix provided people with a training data set with movies, ratings, and so on. And they provided them a test data set with only the X's. And they said, here is your training data set. Find the best model, build the best prediction, predict the test data set, the one where we don't see the variable y. And we are going to compare your predictions to our Netflix predictions. But Netflix had the y's. Netflix could observe the y's. So then they could compare their predictions of the y's with the predictions of the other teams. But the other teams could not observe these y's. And model averaging is what the winners used. They had all kinds of models, very flexible models that allow for very erratic or not movements. They use cross-validation a lot for many of them, I believe. And overall, it's an average of many different models that produced the best predictions. And model averaging is a very powerful tool, same as cross-validation. That's going to help us understand how machine learning algorithms function. That's it for this lecture on model selection. Remember that model selection is part of machine learning. The idea is that once you program a model selection algorithm, you just have to submit the dataset to your machine, to your software, and the algorithm is going to automatically find the best predictions, the best model, and so on and so forth. The more data you feed to the machine or the software, the more it is going to learn, because the more it is going to train on data. That's it for this lecture. Have a good rest of your week and see you in the next one. Bye.